Okay, the last year we discussed how to use basically the simple roots to complete the full root system. We also hinted us on how to find the algebra from just the simple roots, although we have not done that in detail. So what we are going to do today first is talk about a separate way of essentially doing the same thing, of creating the entire root system from the simple roots. However, this is essentially the same thing that we did the other day, except that instead of being geometric, it's more algebra-like, which has the advantage that is easier to keep track of. And for example, if you ever wanted to automate the process and write a computer program to do it, it would be easier to use this particular approach. It's also easier to keep track of whether you are actually exhausting everything or not. That is, you're finding all the roots or not. Okay. So for this, just to remind you that if we go back to this, so we have the simple roots, and let's say we are going to call them alpha 1, alpha 2, and so on. And in a m-dimensional, m-rank Lie algebra, where the Kartas are, there are m Karta generators, you're going to get exactly m number of simple roots, right? Because the simple roots are linearly independent in that space. Well, if you were to be mathematically very finicky, you would actually say that the roots do not reside in the same vector space, it resides in a dual vector space and so on. But for finite dimensional vector spaces, it hardly matters. So if we wanted to do this more precise mathematically, we would have said that, okay, the Karta generators span a space, and even the Lie algebra generators themselves span a vector space, and then there's a dual vector space to that, and the dual vector space is where the roots and weights live. However, since finite dimensional vector spaces, frankly, as long as the dimensions are the same, they're isomorphic, we are not going to go into those details right now. But just to remind you what these roots are supposed to do, these are of course simple roots, but all positive roots can be made by non-negative integer combinations of these, and all negative roots, of course, are just negatives of those positive roots. So all roots can be figured out from combinations of these. And if you picked, say, the SU2 algebra due to, say, alpha I, of course, that means alpha I minus alpha I, the pair, and alpha I dot H, all three together with the appropriate scalings, and took this and applied it to, say, any weight, to any eigenvector of all the HIs. We know what happens here, especially if we apply twice E3 to this. You are going to get twice alpha I dot H, because when I say H, it really is an H vector, because there's one for every H. So that's what the dot really means here. Okay, I'm not going to just put arrows on top. That's disconcerting. So by alpha I mod square acting on the state mu, and that ultimately gives you alpha I dot mu by alpha I mod square. That's something you all know. What is important is also this number essentially tells you how many gives a difference of how many times you can lower this and how many times you can raise this. Right? Now, what is important is, if you want to, so whatever information there is in the mu, if I give you all the qi minus pi's, that is, of course, you have to give them for all the mi's, then my claim is whatever information there is in a weight vector. Of course, a weight vector, remember, is a vector in m-dimensional vector space, so has m components. qi minus pi, how many numbers are these? These are, of course, m numbers, because one for every simple root. So there, of course, the number of components of mu and the number of these qi minus pi's, they match. But just because you have the same number doesn't necessarily mean that they have the same information always, right? Say, x equal to 1, y equal to 0. These are two numbers. Now, if I gave you x plus y equals 1 and 2x plus 2y equals 2, that's also two numbers, right? But knowing this, you can of course find out this. From the left, you can go to the right, but from the right, you cannot go back to the left, right? So just because you have two numbers here and two numbers here doesn't mean that they carry the same amount of information. This one has more information, the one on the left. The one on the right has less. Is this clear to everybody? So just because mu has m components, mu1, mu2, all the way up to mu m, and you have q1 minus p1, q2 minus p2. These are of course integers, single integers, up to qm minus pm. There are m numbers on both sides. That doesn't necessarily mean that they have the same information. Of course, if you know the mu's from that, it's obvious that you can get this. But what should be obvious is that this works. Okay, not obvious, but what should be easy to see, reasonably easy to see, is that they have the same amount of information. Can anybody tell me why? That is, instead of giving the components of mu, you could just as well given me the m numbers qi minus pi that will have exactly the same information. Is this something you can see, or does this require an explanation? Yes or no? Yeah, I need to know from you
Yeah,
whether.
I
Hmm?
need some explanation. I mean, I can't imagine. Some...
Okay. No, this is okay, right? The fact that these two don't have equal amount of information,
Yeah, that's okay.
that's okay, right? So it's easy to see that you can go from here to here, but not back. Here I am claiming that if you took each one of the simple roots, remember there are m simple roots in your rank m Lie algebra. If you have m Karta generators, you will have corresponding m simple roots. And these m simple roots, when they go and act, or not the m simple roots themselves, but these SU3 generators, SU2 generators which you make out of those m symbol roots. So alpha 1 dot m, alpha 2 dot m, etc., scaled by alpha 1 mod square, alpha 2 mod square, etc. When they go and act on your states, you're going to get some integer in front. In fact, you would get a half integer, but you have deliberately put in a 2 to end up with an integer. And this integer we know can be interpreted as qi minus pi. That's fine. That I hope is clear to everybody. My claim is that if you know the qi minus pi's, from that you know the mu. But why is that the case? What you are claiming here is that essentially, if you tell me the qi minus pi's, you know the projection of the vector mu in the direction of each one of the alpha i's. Is that enough to reconstruct the alpha i's? That's the question. Sorry, is that enough to reconstruct the mu's? The alpha i's are known, so you have a particular Lie algebra which has a bunch of simple roots. If I give you the
Yeah, I've
projection of
got.
mu in the direction of each one of the alpha i's, is that sufficient to tell you what the mu's are? Yeah,
Yes, because alphas constitute a basis of the space. I've got it.
exactly. Right. So one thing is important. These numbers are not actually the coefficients which sit in front of alpha i's. This is one thing you have to be clear about, because we're so used to dealing with orthogonal basis systems, right? Basis vectors which are perpendicular to each other. So when you take the dot product of the basis vector with the vector, you essentially get the component in that direction, right? Okay, right? That's what you have, right? Usually, if you take the dot product with say I, you are using ijk in 3D. If it, hold on, just give me a minute. Okay, sorry, that's not what I wanted to show you. This is what. So, so the one thing is important. If you know all the projections of all these components, you actually can reconstruct mu from here. But the reconstruction is not as simple as just take these coefficients, put this in front of alpha i's and sum up. Is that okay? Yes, because we are using non-orthogonal vectors. Alpha 1, alpha 2, alpha 3, or whatever the algebra gives us, they are not necessarily perpendicular to each other. Usually they won't be except for very special kind of Lie algebras, right? Yeah. Any questions about that? By the way, if you have non-orthogonal vectors and these dot products, what is the easiest way of reconstructing the mu from the dot products? Using these numbers? Any idea? You've actually done this. The reason why I'm asking you is you have already done this in some course. If you have vectors which are not orthogonal to each other, but they form a complete set, then what is the easiest way to reconstruct the vector from the dot products of the original basis vector with that? You've done it in some other course. Suppose you have a bunch of vectors, let's say a1, a2, a3, which are not orthogonal to each other. Okay. And there's a vector v, which is, for which you know a1 dot v, a2 dot v, and a3 dot v, these numbers. That's essentially what we are saying here, right? So v can be written down as n1 in terms of n1, n2, n3 being the coefficients of three vectors, which are not a1, a2, a3, by the way. But what property do these vectors b1, b2, b3 have to have? And have you ever seen these vectors being used? Nothing to do with group theory, or actually a lot to do with group theory, really, or rather linear algebra, which is something you use in group theory. But in fact, I deliberately wrote A1, A2, A3, B1, B2, B3 to remind you of this. You must have seen this before. By the way, if you look at this and work backwards, you should be able to figure out what A1 dot, if this has to work for every vector V, what should A1 dot B1 become? Can anybody tell me that? Or in general, AI dot Bj, what should it be? What should it be for this to work? That no matter what vector you have,
delta ij.
delta ij, right? And does that tell you what the BIs are? The B1, B2, B3?
Reciprocal
Yeah, reciprocal vectors. You use them as in the context, so you would typically call them reciprocal lattice vectors, simply because you use them in the context of solid state lattices. But that has nothing to do with solid state. This is just these are basis vectors which essentially help you to map to the dual space. So if you have a vector space and you have a dual, and you can have this dual basis which is given by epsilon I, ej is delta ij. These are that gives you the dual basis vectors. That's the easiest way of expanding things here. So that's all I'm saying is these coefficients, which are the qi minus pi values, they're enough to tell you what mu is. But mu will be essentially these coefficients times some vectors which are actually reciprocals to the alpha i's. Is that okay? But for us, what is important is not even the procedure to reconstruct the mu. What is important is this understanding that knowing Q1 minus P1, Q2 minus P2 up to Qm minus Pm is the same thing as knowing the mu. So the Qi minus Pi values have exactly the same information as the weight vector has. Is this clear?
Yes, sir.
So now, of course, this is for a single weight vector. Now you could do this for every one of the weight vectors, right? So every one of the weight vectors which describe a particular representation, you could have Qi minus Pi values for that. And that's actually going to be very important later on when we try to create all the representations. But for the time being, let's focus on a special case, which of course is a standard special case for weights we always focus on, which is the roots themselves. Or even more, just the simple root. So if mu is one of the simple roots, then what happens? Then Qi minus Pi, these values will simply be twice alpha I or alpha j by alpha I square. Of course, this is the Qi minus Pi for, okay, this is for shifting the Ej, E alpha j along alpha I, right? So that's the Qi minus Pi value, which says Qi is, of course, how many times you can shift down, and Pi is how many times you can shift up. By the way, now that we have actually defined positivity and so on, we can, without sort of feeling very stupid, we can talk of raising up and down. Okay. Now the important point is that this of course gives us, these numbers tell us what happens when you try shifting the simple roots, and they have as much information as the simple roots themselves, as we just argued, because from these you can reconstruct the root vectors as well, and simple roots, and then from them all the roots. So this set of numbers is actually, of course, given this, you should see that when I've written Qi minus Pi here, but this is Qi minus Pi for E alpha j. Of course, that means this depends on both indices I and j. That's clear from the right hand side. And this is what you can easily use to define an object with two indices, which of course is a matrix. Okay. So what you have here is an R by M matrix, where M is a rank, A, whose elements are given by this, and this is called the Karta matrix. As I claimed that the Karta matrix essentially gives you the entire information about the root structure, and this is what we are going to use to figure out a way for recreating the entire root system. Okay. So how this works, I'm going to detail the procedure for you, but first look at some of the standard Karta matrices. SU3, which remember is this, and the Dinkin diagram given by this, will give you a 2 by 2 Karta matrix, simple enough thing. And this 2 by 2 Karta matrix will be given by, now the numbers are very easy to figure out. You can of course look at the roots themselves, okay, and figure out what the numbers are going to be. But one important thing is for every Karta matrix, the diagonal elements, how much are they going to be?
2.
Yes?
2.
How much are the diagonal elements going to be?
2.
2, right? Obviously, has to be 2. And of course, it has to be 2 because you can see from the value. You can also say that it has to be 2 because it's basically the Qi minus Pi value for how many times you can shift down or up the E alpha along the direction alpha, right? Now, how many times can you shift up the E alpha in the direction of alpha? Okay, that's
Once.
a p. That's a p value.
One.
No, you can't. Zero. Because E alpha, that's the E, you're talking about E alpha, right? Can you shift up E alpha in the direction of alpha? If you could,
Oh,
you would end up
okay.
with 2 alpha.
Yeah.
And that's not a root, right? So P is 0. And how many times can you shift it down?
Twice.
Twice. Because basically, this is simply saying that for each SU2, the generators themselves furnish a spin 1 representation. E alpha is the highest weight state. Alpha naught H is a 0 state. E minus alpha is the lowest weight state, which cannot be lowered any further. So this 2 is natural both from the point of view of how many times you can raise or lower, or simply from the formula itself. Now, the off-diagonal elements, of course, they need a bit of thought, but they are very easy to figure out. For the SU3, where the angle is 120 degrees, and both roots are equal in length, this is pretty straightforward. You just put this in, it's just cosine of the angle in this case, right? And it's going to be minus 2. Sorry, 2 into minus half, which is minus 1. That's SU3. G2, our other example that we talked about, well, that's again 2 by 2, but that takes a bit more thought because, of course, the angle is 135 degrees, sorry, 150 degrees now. So to calculate this a bit more carefully, and the two roots are, symbol roots are not equal in length, so the off-diagonal elements are not going to be equal. So just work this out. It's pretty straightforward. That these are the numbers you're going to get. You can just use the actual root vectors which you wrote down and just take the dot product and find out these numbers. But all I'm saying is, even from the Dinkin diagram itself and the basic rules about how long the ratio of the lengths and so on, you should be able to figure out that this is going to be the matrix, Karta matrix. So these are the Karta matrices for SU3 and G2. Okay, Georgia gives one more example of a more complicated algebra, or more complicated simply because it has more simple roots. So this is this one. 3 simple roots. This algebra is called C3. The reason for that will be clear later, but reason for this nomenclature. But this is basically alpha 1, alpha 2, alpha 3, 3 roots. And this is the Dinkin diagram for that. What this tells you is that basically, okay, what does it tell you about the angle between alpha 1 and alpha 2?
120 degrees.
This, remember, is at 120 degrees. And alpha 2 and alpha 3? That's again straightforward. What are the possible values? 90, 120, 135, 150. So alpha 2, alpha 3 is what?
135.
135.
135. Yeah. Well, what about the angle between alpha 1 and alpha 3?
90.
90. Right. Exactly. Because there is no line between them. Okay. So basically, this is a 3 dimension. Remember, this is in 3 dimensions now. So alpha 1 and alpha 3 are 2 perpendicular vectors, and alpha 2 is a vector which makes an angles of 120 degree and 135 degree with them respectively. And from the formula that we have derived before, you can also figure out what the lengths are going to be. And this, of course, is going to give me a 3 by 3 Karta matrix with diagonal elements 2, 2, 2. Well, this is sort of easy to understand. This is basically what you get for SU3 part, the single bond thing. And for this double bond is again easy. Actually these numbers are pretty easy to write down. They're just, the lower one is essentially related to the number of bonds here. Okay, what will go here? There's a 1, 3 element. So what will go here?
-1 in the top and 0 in the bottom.
No, it's 0.
0 both of
No
them.
place. Come on, the numerator is alpha I dot alpha j. The denominator differs, right? Denominator can be alpha I mod. So, for example, why are these two numbers different? They have the same denominator. Twice alpha 1, this is twice alpha 2 or alpha 3. But in one, the denominator is alpha 1 mod square, the other is it's alpha 2 mod square, the other is alpha 3 mod square. But here you have alpha 1 dot alpha 3 in the numerator, which is 0 because the angle is 90 degrees. So this has to be 0 anyway. Okay. So these are 3 examples. You can write down Karta matrices for any such Dinkin diagram. Now, the question is, what good does it do to you? The thing is, you can build up the entire set of roots very easily from the Karta generators, and next day, I don't have the time to cover the rest, but today. But the next day, we will see how can you use this Karta matrix to also find out all representations. That is not just the adjoint representation, which will give us all the roots, but also arbitrary weights. So for the time being, and this procedure is really trivial. Basically, what you do is you start with the simple weights, and for that, right, need some space. Okay, so 2 minus 1 minus 1, 2. That's easy to remember enough. So 2 minus 1. Okay, what I'm doing is I'm going to say there are 2 simple roots, alpha 1 and alpha 2. And these rows, remember we wrote AJI as twice alpha j dot alpha I by alpha I mod square. So basically we were saying, look at the root E alpha j and ask what kind of shifting can alpha I do to it, right? So now, of course, in a matrix, J is the row index. So basically, this 2 minus 1 here, this stands in for alpha 1. What this tells you is what can you do on alpha 1 using alpha 1, that's this element, and using alpha 2, that's this element. Is that clear? The question is, using the SU tools with the different simple algebras, what can you do to these roots? So this 2 tells us something about what alpha 1 can do to this, and this minus 1 tells you something about what alpha 2 can do to this. Both cases, we are talking about alpha 1 being shifted either in the alpha 1 direction or in the alpha 2 direction. This minus 1 too, the minus 1 tells you what you can do with alpha 1 on alpha 2. And this 2 here tells you what you can do to alpha 2 using alpha 2. So, is this clear? That's one thing which you have to, maybe I didn't say this clearly enough, but that is what you really need to understand properly. So these numbers essentially, okay, these numbers don't tell you how many times you can shift. Of course, these give you the Q minus P values, right? How many times can you go down minus how many times you can go up. But for what? This 2 tells you how many times this is for alpha 1 and this is for alpha 2. This 2 tells you how many times you can go, the Q minus P values for shifting alpha 1 using alpha 1. This is Q minus P value for shifting alpha 1 using alpha 2. Is this clear?
Yes.
Okay, and just to make this sort of easier to follow, these are basically simple roots. Okay, so remember our notation, this is the 1 level root, right? Well, there is a 0 level root which we didn't talk about. 0 level roots are not roots at all. They are the Karta subalgebra elements. Okay? And all Karta subalgebra elements, no matter which ones, they have 0, 0 values. Now, the point is, this okay, this is not so obvious at this stage because this doesn't really look very informative. But what this really tells you is how many times can you shift. So this is 0, 0. This is the, of course, in your original root diagram, this was at the origin. That's where the Karta generators lie. They don't have any non-zero eigenvalues. The eigenvalues are all 0. And then you shift, right? Then you shift to get alpha 1 in the direction of, or you could shift to get alpha 2. The suffix, of course, essentially tells you that these are the two different weight vectors that you're different root vectors, symbol roots that you're looking at. Okay. So here the shifting thing will be essentially shown by arrow. So if you are shifting, so this is basically, okay, the arrow which I'm going to draw is going to look like this. You shift up this one in the one direction to get here. And you shift up this one in the two direction, you get here. So these are two arrows which keep track of which way you're going. Shifting, so shifting using alpha 1 is this vector. Shifting using alpha 2 is an arrow in this line in this direction. You don't even have to draw an arrowhead. Okay. So far, no new information really has come up. It's really just that much. Then what you say is, okay, you investigate what happens here. Now, this is an important question. The 2 here essentially tells you that you are done. You can't shift this up any further. Why? Because simple roots, remember the diagonal elements essentially, okay, this is something you don't even have to work out because you know that these cannot be shifted up. Why? Because these are alpha 1. If you shifted it up, it will be twice alpha 1. Or this one, if you shift it up, will be 2 alpha 2, which of course can't be done. Okay. The other way to look at it is this is just a q minus p value. And the q value for these are actually 2. Right? For both this and this. As you go down, I'm not drawing the other side, but there is another element on this side, which I could have drawn. Okay, and there's another element on this side, which are basically the minus alpha 1 and minus alpha 2 roots. Is it okay? So this can be shifted down twice, q of 2. Of course, that means q minus p of 2 means p is 0. Okay, that's sort of easy. And you don't, so basically, once you have a 2, you don't worry about that any further. At least the diagonal element, this corner elements, they can't be shifted up or down anymore. But what about the other ones? Okay, what is the q value for this? What's the q value? Remember, when you're talking q value for this, you're asking second component, right? That means you're saying, how many times can I shift this down using alpha 2?
0.
Yes?
0.
0. And similarly, what is the q value for this? So how many
0.
times can I shift this down using alpha 1? So q values for these are obviously 0. And that's easy to see also on the diagram because there are no lines coming this way. Right? That would be a shifting down by a line this way. If it had been there, would have been shifting down using alpha 2. A line this way would be shifting down using alpha 1. No such lines, no q's. So no q's, of course, this means the minus 1 here means p is 1. So the p values are just negatives of these. The off-diagonal elements are just negatives of the p's right now. So you can shift this one along alpha 2 up once. Okay, so this is something we already know, of course. For SU2, there's nothing very new that will happen. So, but that is drawn by a line which is parallel to this. I just draw a line which goes like this. That is along alpha 2. Well, what about this? You can shift it once, right? Along alpha 1. So, okay. Like this. But of course, no matter which one you do, whether you shift alpha 1 along alpha 2 or alpha 2 along alpha 1, you end up with the same result, right? Which is
Phi 2.
Yes, you get something in phi 2, but moreover, what you get in phi 2 is simply alpha 1 plus alpha 2, right? Nothing more. Either way. This again is something we have already done before. It's just that we are using this using the Karta matrix language. And for SO3, it's so simple that the Karta matrix language doesn't really look like a grade K. But just persist with me, you will soon see why it's important or is useful. But what will be the Karta matrix elements now?
1, 1.
Yeah, it's basically simply going to add up. Why? Because these are just the Q minus P values for this particular root that is sitting here, right? The Q minus P values for the simple roots sit in the phi 1 level, but here you get the Q minus P values for the root. And the important thing is, if you shift from phi to phi plus any alpha, say using the jth alpha, okay, that means you are using E alpha j to shift. Then, of course, the K goes up to K plus 1, right? You get, in particular, in fact, only Kj goes up to Kj plus 1 and all the other Ks stay the same. So total K stays goes up by 1, which is why I've gone up from phi 1 to phi 2. But what is important is what happens to the Qi minus Pi values? Well, Qi minus Pi values, remember, are nothing but twice alpha I dot whatever mu you had by alpha I square. So now the mu has changed from whatever you had earlier to an extra alpha j. So whatever you had earlier, that will be there. Plus what will happen? You'll have an extra twice alpha I dot alpha j by alpha I square.
12 points for being polite. But I didn't quite catch your question. Would you be a dear and repeat it, please? By the way, when you see the yellow light ring on your device, it means you have a notification or message. Just say, read my notification.
Alexa, stop. I don't know why, don't know how it could think that I was talking to it, but anyway. Okay, sorry, that was an echo dot thinking that I was talking to it. Did you hear that? Or I hope you didn't.
Yes.
We
You
heard,
did
sir.
hear that. Okay. Okay. Thankfully, it was giving me full marks for being polite. I don't know. Anyway, let's come back to this. I just lost track of what I was saying. Okay, so you get this, right? That is, you had this in one level, you had some root phi. You shifted it using alpha j. That's what you're doing here, either using alpha 1 or alpha 2. You're shifting. And what happens to the Q minus P values? Q minus P values are just twice alpha dot mu by alpha square. The new mu, of course, the old mu was phi. They have added an alpha j to it. So the old mu gave you Qi minus Pi. The added term will give you this extra. And what is this extra term? That's just but AJI, right? So if you add alpha j, you are going to get an extra. The jth row is going to be added to whatever you have now. So these are the Qi minus Pi values. If you shift it according to E2, then the 2th row, which is this one, will be added. Or if you start with this and you shift it using E1, then the 1th row, which is this one, will be added. Either way, you will end up with 1, 1. Okay? Is that clear?
Yes, sir.
Now the question is, these are the Q minus P values. How much is the Q here? This is this Q for the first, for alpha 1. It's 1 because you see you can go down once, right? That means the P value here is 0. What's the P value here?
It's the same, right? Q equal to 1,
Yeah.
P equal to 0.
Right. Q equals 1 because there's one line joining this, which means you can go down once. But since Q minus P is 1, that means P has to be 0. So this means that you have come to an end here. You cannot go up any further. All positive roots possible for SU3. Not very impressive, right? I spent a lot of time discussing this, but at this stage, you just had 2 steps to work through, and that's it. Doesn't really look very impressive, and moreover, we had already done this before using the root diagrams, and this doesn't really look like a huge advantage. But to see what kind of an advantage it can be, let's just look at the G2. This is the Karta matrix. Okay, so for this, to start at the lowest level, this is not the lowest level, this is actually the middle level. There are negative roots below this, but I don't really bother drawing the negative roots. Okay. Then you will take these are alpha 1, alpha 2, or which we called alpha and beta in the last class anyway. This is the k equal to 1 level. This, of course, is the k equal to 0 level, where no symbol roots are there, just the Karta generators. Now, the question is, how many times can I shift up? Okay, how many times can I shift this up along 1? The answer is 0. And that, by the way, is always the case for the diagonal elements at k equal to 1 level. So, frankly, I don't even need to bother thinking about this too much. But how many times can I shift this up in the 2 direction? Come on. Okay, let me just first draw the arrows. How many times can I shift this down in the 2 direction?
In the two, like shifting down alpha 1 in the direction of alpha 2.
Yeah.
That is 0.
Right. So how many times can I shift this up?
Once.
Once. How many times can I shift this up along alpha 1? Remember, this is alpha 2. And when I'm looking at this, the first one, I'm asking how many times can I shift this up along alpha 1? So this is how many times?
It's gonna be thrice.
Thrice. Exactly. Q minus P. That's it. Q is 0, P is 3. So this one can go up thrice in this direction. This one can only go up once in this direction. So once in this direction. Of course, what I'm going to get when I shift this once in this direction is going to be 2 plus minus 3. Remember the Q. That means to this vector, I'm going to just add these numbers. AJI is going to be added. So this is going to be minus 1 and this is going to be 1. Okay. That's, of course, alpha 1 plus alpha 2. Okay. Well, you can shift this up in this direction as well, which is just here. But then you can go on. And what will this be?
1, 0.
You can go this minus 1, 1, to which you're going to add this thing, right? Which is going to be 1, 0. What will this be?
3 minus 1.
By the way, at this stage, you should also look at what can you do along. Can I go along this?
We can't.
Why not?
Because we can only raise alpha 1 along alpha 2 once.
True, but you can see it from this as well, right? Q minus P of minus 1, right? But P is already 1.
Yes.
Okay. And then what about this one? Can I go further? I can't. So what about this? Here, the 1 actually tells you that there is a P of 2 here. Sorry, Q of 2. For this thing, there's a Q of 2. Q minus P is 1. That tells you that P is 1. You can go this further. But I already knew that. I went all the way up. But can I go this way? Is this possible? Okay, this is for shifting this along alpha 2, right? What is the Q value for this? Remember, because I've drawn this diagram in stages, I know exactly what happened in the previous stage. Previous stage, you had only alpha 1 plus alpha 2, nothing else. You couldn't have this. Do you have anything on this side?
Q and P should be same. So if they are non-zero, then we would have another root on the phi2 level.
Yeah, the point is Q cannot be 1 or Q is already 0. I can see that. There is nothing here, right?
Then P is also 0.
P is also 0. You can't raise this. What about this one? On this side, there is no Q. I can see that. I didn't have to draw this to and then cut it away because I didn't. The very fact that I didn't draw it till now means that there is nothing on this side. But what about P for this?
It
P has to be 1, right?
P has to be 1, right? Q minus P is 0. Q minus P is minus 1. Q is 0. P has to be 1. So which means you can actually move this way. This is the other one which we would have missed otherwise. Okay? And when you move it this way, what are the Q minus P values? What is this vector going to be? 3 minus 1 is what you had. You are moving this way, so you have to add minus 3, 2. So this gives you 0 and 1. Right? Is that okay? To 3 minus 1, you're adding this. Because you're going this way. So you're shifting using alpha 2. So you're going to essentially add the second row of the Karta matrix. When you're shifting along the ith alpha I, you're going to add the ith row of the Karta matrix. That's it. But now, here, of course, along this, there is no Q. That means since it's 0, there's no P. So P is 0 for this. Along this, what about along this?
Q is 1, P is 0.
Q is 1, then P is 0, right? Now that you have hit a P 0 at both levels, you can't go up any further, right? That means these of course are the Karta generators, but this, and this. These are all the roots. Is it okay? I think you need to play with this a bit to sort of be comfortable with this. But what I will try to urge you is work this out yourself without looking at the book. Of course, all this is in Georgi. But I would suggest that don't look at Georgi. Try to do it yourself first. And then check whether you got it right. Okay, final example. Let's do this quickly. I don't have much time before I have to jump to the meeting. This is for the C2, the C3, sorry. This particular LinkedIn diagram. Of course, this is three-dimensional. Now, this is where this Karta algebra method becomes even more important, because once you get to ranks higher than 2, if you were to draw this on the vectors and use the previous method, you would have to, in this case, draw a three-dimensional diagram, which becomes difficult to sort of handle. And of course, if you had ranked more than 3, then you're in deep trouble, because then you wouldn't even be able to use that method, at least not visualize using that method. So this one is straightforward. What you do is start at the 0 level. On the 1 level, put the 3. Okay, maybe I should actually give myself a bit more space. Just hold on. Class check to body করছি. So the three roots alpha 1, alpha 2, alpha 3 are characterized by these q minus p values, essentially these three rows of the Karta matrix. And basically you're saying that if you started from alpha dot h and shifted along this, you're going to get here. And so three directions you can shift it. Now, no further movement in this direction, no further movement in this direction, no further movement in this direction. These tools essentially tell you that you have reached the end, right? But how many times can you move up here?
Once.
The middle one is up.
Once.
Yeah, this is once. How many times can you move this way? That's the third index. The q minus p value is
0. You can't move in that direction.
0. You can't move. So there's q minus p is 0. Q is 0 because you didn't have anything on this side, so p is 0. Right. So what about this one? How many times can you move this way?
Once.
Once. So essentially parallel to this. How many times can you move up? None. Right? Is it okay?
Yes, sir.
There's two here. Two here simply tells you can't move up. By the way, you can see only one line on this side, but there's another line on this side for the negative of this. So can't move any further anyway. Okay, here on the other hand, so this one, no movement this way. No, okay, the movement this way, no movement this way. This on this side, once, right? Just a negative of this. So what are you going to, and what about this one? How many times can you move this way? Not at all, right? That's a 0. How many times can you move up?
Twice.
Actually, twice. There's the -2 here. That says you can move twice up. That's it. So, of course, here, if you were to move like this, what are you going to get? You're going to get to this by either saying that, okay, I'm moving this way. That means I'm going to add this row to this one. Or you're moving this way, which means you're going to add this row to this one. Either way, you get the same result, which is 1, 1, minus 1, right? There's, of course, alpha 1 plus alpha 3. Sorry, alpha 1 plus alpha 2. Right? This is alpha 1, this is alpha 2, this is alpha 3. And here, of course, you are getting alpha 2 plus alpha 3. So these are the only two roots at the phi 2 level. Alpha 1 plus alpha 2, alpha 2 plus alpha 3. Okay? Alpha 1 plus alpha 3 is not a root at the phi 3 level. That would have been not so easy to figure out. You would have to work rather hard to figure this out, but here it's sort of easy to see. So what is this going to be? This is going to be -1, 0, 1. Well, what about this one? You're shifting this up, right? That means you're going to add -1, 2, -1 to this. So -2, 2, 0. So let's look at, now we are going to examine each of these roots and see how many times can we shift them. Well, how many times can I shift this way? Well, we can't. We know that because we already knew that because this -1 told you that you can shift this in this direction once. So you can't go any further. Or you could just say that, okay, the q minus p value here is 1, q is 1, so p has to be 0. What about this? Can I shift this up?
No.
Same argument.
No, because again, same argument. Either you could use the fact that this -1 told you could shift this up only once, or you could just use the fact that q minus p here is 1 and q is already 1, so p is 0. What about this one? Can you shift it this way?
Once.
Once.
Once, exactly. So you end up here. So again, at the 3 level, so this is another vector at the 3 level, this is another one. This, by the way, is shifting alpha 3 twice in the alpha 2 direction. So that's what you have here. And here, what you get is simply this plus this. So that's 1 minus 1, 1. Of course, what about these? Can you shift this any further? Of course, you can't shift this any further. You can shift this once. You have already done that. How many times can you shift it in this direction?
Once.
Yeah. And that's exactly where you are going to land up with. Right? So there's alpha 2 plus alpha 3 shifted once in the alpha 1 direction. That's alpha 1 plus alpha 2 plus alpha 3. Of course, it's also alpha 1 plus alpha 2 shifted in the alpha 3 direction, which is the same. But does this end here? What about this one? How many times can you shift this? Can you shift it up?
Minus 2.
For that, you have to look at the middle one. It's already 2, but remember, you've already done it twice, and moreover, you can see the Q is 2. The Q minus P of 2 will tell you can't go any further. This, by the way, this 2 is not a diagonal 2, so you don't use the same argument that diagonal 2 means can't be shifted. Here, all you see is, okay, I have a 2 here, but I've already done twice. So two Qs, P of 0. What about this direction? Of course, the 0 here tells you can't. What about this one? There's a minus 2 here. So how many times can you shift this way?
Twice.
Twice. Right, so you actually have 2 shifts possible. And you should be able to see, okay, I'm running out of time, but you should be able to see when you complete this, that these are the only possibilities. So for the C3, you have 1, 2, 3 simple roots, then 2 roots at the phi 2 level, 2 again at the phi 3 level, 1 at the phi 4 level, 1 at the phi 5 level. So 1, 2, 3, 4, 5, 6, 7, 8, 9 positive roots. Of course, that also means 9 negative roots. And that also means 21 total roots, right? Or 21 generators. 18 roots and 3 Karta generators. So these are 21 generator algebra. And the claim that I'm making is that one part of which I've already shown you can find out all the roots simply by doing this process. And the other claim I'm making is that you can find out the entire algebra, which means all the commutators of the 21 generators among each other. That's quite a huge number, just from the information that is there in the simple roots, which in fact is just from the Karta matrix. You don't need any further input. For semi-simple Lie algebras, the Karta matrix contains complete information about how to build up the algebra. So we are going to take a look at building up the algebra in the next class, which will be next Wednesday. From 10 as of now, but if something comes up again, then I'm going to ask you to shift it up by half an hour, let's say. And we'll have a class the Friday after that. And hopefully that will be enough to wrap up this part. Okay. By the way, I'm going to start putting up my lecture videos for the formal course, PH5102 soon. Now, most of these will be essentially the same video, same things that I've told you, except that they should be in a more polished format, because I'm doing this beforehand. But that may not be better, but it's just going to be, edited. So let's see. So if you're interested, you can take a look at them as well, although you've already seen most of the material. Okay, now I have to run today. Okay. Any quick questions I can answer, but I have to really run. So if there are no quick questions, I will just stop the recording.